down the sides of it, like it's tender. It's not inside the sores, just on the muscles on the outside.
She's it's really stiff.
Yeah. Well, you're gonna have days like that. It's just, it is. When did you have yours done?
April 17th,
Oh,
it's just 2 months.
Yeah,
But you know, my first one 10 years ago was nothing.
Yeah.
Yeah.
It's funny how things happen and things with the body, and our body's a funny thing.
All right, good morning, everyone. Looks like we're still waiting for a few participants to join. We'll give them 1 or 2 more minutes, but I'll start by introducing the panel this morning. My name is Ben Boyer. I'm the production manager at Kiwi Orthotics. We'll also be hearing from Dr. Kelly Robb and Dr. Michael Ryan and Alex Rayner, whom a lot of you are familiar with since he handles most of the day-to-day client interactions here at Kiwi. So let's get started. Today we'll be talking about 3D printing and what it means in orthotic manufacturing nowadays. So just a basic run of show for today's webinar. We're going to do a brief overview of what 3D printing is and how it works. And we'll talk about how it can benefit patients, how it can benefit your clinic and your business, and what Kiwi's been doing in the 3D printing space. If you do have any questions, please feel free to put them in the chat. We'll do the Q&A session towards the end of the presentation. So let's get started with what is 3D printing. So also known as additive manufacturing, there's various different methods that all kind of have in common. They deposit material in layer by layer to build up a 3D object. The 3 main categories of 3D printing are fused deposition modeling, FDM. There's various methods that I class under powder bed printing, and there's photopolymer resin printing. There are a few other methods that exist as well, but these are kind of the 3 main categories. So taking a closer look at fused deposition modeling, this is the one that most people are most familiar with. Fused deposition modeling, I often describe it as a robot with a hot glue gun. So you can see in the image on the left there's a nozzle that extrudes a thin line of molten plastic as it traces out the shape of the object layer by layer. So it traces out the shape, leaving behind that plastic, and then it moves up to the next layer, moves up to the next layer, to ultimately end up with the fully solid object. These are very, very common. Most schools and libraries have 3D printers that students and the public can use. A lot of home hobbyists have these at home as well. And there's a huge range of scale and price and quality with these. The image on the right is one of the most popular consumer level 3D printers. It's a Creality Labs Ender 3 Pro. Very common home scale printer. This method of printing can be used for orthotics and is used to create orthotics. The next method I want to talk about is powder bed printing. So this one is not as familiar, not as commonly known. It's more an industrial scale of 3D printing. The way this one works is a big vat of, or vat is probably the wrong word, a big hopper of powder material is held just a little bit below its melting point. Then the machine spreads out a thin layer of that powder, and then a laser or some other method selectively heats up the spots of the powder that are going to be part of the final part. And those spots melt together and become solid material instead of powder. Then that section drops down a little bit, a new layer of powder is leveled over top, and the process repeats layer by layer, bringing it up to creating the final part. And then when it's done, you have your parts all stuck in a surrounded by the unused powder, which then gets shaken off, scraped off, dusted off, and reused again for the next print. This method can use a huge variety of different materials. Plastics are common, but you can also use various metals and even some pretty exotic alloys. And because of the possible scale of this method, along with the materials available, it's used in a lot of industrial and fairly advanced applications. There's parts in some of the more advanced jet engines that are produced this way. Entire rocket engines are produced this way, and many other parts. This method can be and is used for orthotics as well as knee braces. There's a lot of custom knee braces that are produced this way now. It's a pretty good use case for it. There's also AFOs and some interesting casts for fracture fixation that are created this way. I've even seen some prototype implanted objects like bone graft replacements printed out of titanium or stainless steel. A pretty interesting method. This next slide shows the just an example of some of the parts that this method can produce. So the third big category is photopolymer resin. So photopolymer resin is the first really industrialized method of 3D printing. Started back in the early 80s. And there's actually, I forget what movie it is, but there's a movie from the early 80s where the opening scene is the lead character. I think it might be Predator or something like that. The lead character is being printed on a photopolymer resin printing. So tried looking up what movie it was yesterday, but couldn't find it. Anyways, the way this one works is similar to how powder bed printing works, except using liquid instead of powder. So you have a liquid plastic resin in a bucket, essentially. And the resin is sensitive to ultraviolet light. So then an ultraviolet laser, or there's a couple of other ways of doing it other than laser, but ultraviolet light hits the resin in the spots where it needs to be solidified to make the part. And the resin reacts, becomes solid plastic. And then the build platform moves to expose fresh liquid, repeat layer by layer by layer. This method, just because of the materials available, it isn't really suitable for orthotics. The materials are far too rigid and brittle, so it doesn't work well for an orthotic use case. But it works great for dentures and custom earplugs. Those are two kind of body adjacent medical uses that are commonly produced this way. So yeah, dentures all the time. The earplugs I use every day were printed this way. It's also widely used for extremely high detail artistic models. Architecture it's commonly used to produce architectural models. So those are kind of the three, broad overview of the three main methods of 3D printing. So It's a really open-ended, creative manufacturing method. But the question is, how does that benefit my patients? And that is the question here. How does this benefit patients? So I've been watching this space for well over a decade. I've seen a bunch of 3D printed orthotic tech startups come and go. And for most of this time, I really haven't seen a compelling use case of 3D printing for orthotics. Most of these tech startups that I've seen, really what they've been promoting, what they've been marketing, has been different for the sake of different. There's no real clinical purpose. These startups have all been quite good at burning through venture capital, though. One of the first companies to really make waves in this space announced, like, they first came to market back in 2016. And I've been kind of keeping an eye on them over the years, and they've never really been able to get anything close to a market foothold. I looked them up just a couple of days ago preparing for this presentation, and they're still out there trying to gain market relevance. And just this year took yet another round of venture capital funding. So after 8 years, still relying on venture capital doesn't really strike me as, making a difference. So what I've kind of seen with a lot of the attempts to make a 3D printed orthotics business in a lot of cases, people are trying to sell a product based on the cool factor of 3D printing. And the fact is, orthotics, as good and beneficial and useful as they are, they're not really cool. And even the coolness of 3D printing hasn't managed to make them cool. So that's part of the issue that has come along. So in most cases, what I've seen with kind of these 3D printing startups is a really cool solution looking for a problem. Not really many of these situations have tackled any clinical significance. They're either making really cool looking stuff that doesn't really matter clinically, or they're using the really exciting tech to make kind of the same old thing we've always made. So this does remain a bit of an open question. How does it benefit my patients? A question with a little bit more of a clear answer is, how does this benefit my clinic or business? There's a bit more of an answer here. So at the lab scale, there is some benefit. Once you get to a certain size, there are some efficiencies and cost savings to be had, especially if a lab is not particularly efficient to begin with. You can have a fairly large leap to a much higher efficiency level by going with 3D printing. So far, we haven't, in the Kiwi lab, we haven't had the truly compelling efficiency gain to adopt it large scale, but we're keeping an eye on it. Another possible benefit is that it can be used in clinic manufacturing to a degree. 3D printing does remove a lot of the barriers to traditional in-clinic manufacturing, but it replaces them with different barriers. So with traditional in-clinic manufacturing, you need a lot of equipment and know-how. With 3D printing, you need different equipment and different know-how. So it trades as one set of barriers for another set of barriers. So again, the question remains, there's no really, really compelling reason. So again, where is the benefit? Why are we even doing this webinar today? So in more recent years, there have been a few use cases that have come up that we have found that can make a big, that this production method can make a big difference. And that's what we can look at. So what has Kiwi been doing in the 3D printing space? Well, like I said, I've had my eye on this for quite a long time. For the past 12 years, we have been watching and experimenting and looking for real use cases and printing all kinds of things. So we bought our first printer back in 2012. I first presented on this topic at the Orthotic Symposium in 2013. And in spending a lot of time experimenting and considering what this can do, we have now come to some pretty useful, clinically relevant use cases. And I'd like to speak about two of those use cases before moving on to what this is going to look like over the next few months. So the first of these, Dr. Kelly Robb, who's on the call, she's been doing some research in textured insoles that I'd like her to tell us about. Kelly, I'll hand it over to you.
Yeah, thanks, Ben. We're going to make these awesome again. They're going to be attractive for everyone. We're going to change the narrative a little bit. Yeah, thanks for that. So this really stems just a really 30-second background from some of my PhD work that I've done, where the goal was really to incorporate some type of texture based on what we know and how different receptors in the skin respond. So there was some benefits to specific designs in this texture that we were really trying to target and tried to achieve based on what we know how specific areas of skin respond to these textures when you load it during walking. So there was some neurological benefits and some sensory benefits that we were really trying to achieve. So I was very particular with what I wanted when I first started this. And we ironically started with 3D printing, but in a very different way. And in hindsight, maybe it would have, I never really thought of it until I was thinking through what I was going to share with you today. But we originally started at the university level where we 3D printed molds, and we had different materials that were poured into those molds, and it essentially created the patterning that we wanted. So when we poked the pattern out, it created a flat template of the texture that I wanted. And it was used as a traditional top cover in orthotic manufacturing, as we've done historically. So I was molding a top cover with a 3D printed mold. And then so that was just time consuming and tedious and a lot of gluing, because if I wanted texture in one area versus the rest of the area, we wanted the contours to be smooth. There was a lot of hand labor that was required, but that was the best that I had at the time. And in the meantime, Dr. Michael Ryan, who's on the call as well, and I were outsourcing several different manufacturing companies and material supplies and solutions in Germany, actually, over a couple of conferences over a few years. And we really became challenged with finding something that had the resolution and the detail that we wanted and wasn't an outer sole material often found in work boots. So that seemed to be the only type of material company or, properties of material that even resembled something along the lines of what we wanted. And then that circles back to us working with Ben in the lab. And in that meantime, he had overcome a lot of CAD design hurdles in at least creating the design that we wanted. However, when we would try to mill that, we were getting weak material. It was too thick or too brittle, or it would clog the system. There was just a lot of challenges with that wasn't effective in getting what we wanted. And then that brings us to 3D printing that really had the solution for what we wanted. So once we were able to identify different designs from a CAD standpoint that we needed, we were able to 3D print different areas of texture that we wanted. The entire orthotic could be a textured pattern if we so desired. And then this prototype Ben has shared on the screen is actually the most recent prototype that that he has in person. There you go. That is the most recent prototype that's been printed that's currently being used in my postdoctorate research with Parkinson's disease individuals currently. And so we've now essentially created a solution to the manufacturing problem of designing textured foot orthotics with the high level of specificity that we required or that we desired in identifying where we can place the texture, and it's kind of growing from there. So back to you, Ben.
Kelly, maybe
Thanks,
I'll
Kelly.
add just a little more color behind that as well, because one of the nice solutions that 3D printing provides here is that you can't mill this. You can't get a milling bit that is small enough to, you can mill it, but it won't look like this. It's going to look like someone vomited a bunch of strings of material on top of a EVA base. And so you might think, well, what's the big deal? Why don't you just get a mold and 3D print that and then just overlay that material on top of a contoured insole? And in fact, I remember seeing, I think it was Springer had a variant of a texture that they had at their display at PAC in Halifax this year. And that's fine. But the problem with that is you can't prototype and you can't iterate very effectively, because part of what Kelly wants to do is, this is a highlight of a variation of texture that we think may have balance, but we need to test this. We need to test the type of texture, we need spacing of the texture, its position on the insole, because that needs to map over into certain physiological areas that we think are relevant. And then we need to then change it. And it becomes really difficult to do that when you then need to go and create a die mold out of aluminum, pour that with silicone, and if you want to then actually create that texture. So really interesting application of 3D printing here, both from a manufacturing standpoint, but 3D printing has always been known for prototyping things really well, which it's useful in this use case. Is this a transition over to me now, Ben?
Perfect transition to you.
Perfect. So
what have you been working on, Michael?
So with the one advantage that 3D printing can do that traditional manufacturing can't is the detail at the surface level. The other significant advantage is the ability of 3D printing to, here's the fun word of the day. Anytime I get to use modulate in my day, I feel really smart. But you get to like change, Kelly's laughing. Anytime you get to change the cross-sectional area, so that's like if you cut the orthotic in half and the inside bits of the orthotic, we can change what that lattice looks like. And that's a fundamental part of the technology in our variable density osteoarthritis orthosis insole, or the Voodoo. Right now, this is currently available only to the Kintec group clinicians, and it's something that also is born out of research through my doctorate student, Kelvin C., who worked with Michael Hunt at UBC, and we did a series of, I think we've published 5 papers now that demonstrate the biomechanical efficacy of this concept, that basically takes a lateral wedge, supports it with a contoured arch support, but does it in a way that the two don't cancel each other out. And because of that, we're able to get meaningful and we think clinically relevant difference in the reduction of the knee adduction moment, which essentially relates to joint load on the medial tibial femoral compartment of the knee. That's kind of a big deal when it comes to any sort of biomechanical or clinical measure of the prognosis for individuals with knee osteoarthritis. And at the same time also mitigate the instability that a lateral wedge would create at the ankle. So it effectively works like a unloading knee brace does, but you put it in your shoe. So it, from the standpoint of creating something that has a high degree of patient utility. We're really excited about the implications of a device like this in terms of helping, a condition that affects roughly 1 in 10 Canadians at some point in their life. But we couldn't do this and iterate this again without quite costly either customizations with foam blocks. And I think, Ben, do you have the precursors to this?
Yeah, I have some
that
of
we
the
had used?
earlier renditions.
Yeah, so this is one of the earlier variations that was used in some of the earlier studies that now we're taking what is essentially hard plastizote that has, roughly a Shore durometer of about 70, 75 on the left-hand side, and then like a cloud EVA that has about 20 to 25 Shore on the right-hand side. Now, as you can imagine, if any of you have done any vacuum molding, the density of these materials is quite different. So they are heating up at different points, and having to laminate them in the lab was quite a feat. We could do it, but it was pretty clumsy.
Yeah, these early prototypes were an absolute nightmare to try to manufacture. It took usually about 4 or 5 attempts to get one successful press.
But we still needed it to, like, one of the cornerstones of this is that it's still custom contoured, which is important to help provide that stability to the foot and ankle. Do you have the next image of the blocks that we got from National Shoe? Right. So you can then talk to your, provider for milling blocks, and they were able to speak to their factory partner and then have essentially pre-laminated blocks of material of various density differential that we had to purchase, at a bit of a premium, and it's fine. But because we had to take basically physical blocks of material and then stick them together, that was how we could try to derive at this concept that leveraged a variation in density to really achieve both the unloading effect at the knee and stability at the foot and ankle. So because 3D printing leverages that ability to modulate the interior cross section of the device, it's such a perfect use case here for this. As we look at other variations of this, because we're simply limited by, a little bit more on the CAD design software and our imagination, when you look at the bisection on the bottom planter side of the device here, we no longer need to be constrained by a straight linear line. We can make variations, for example, that can follow the anatomy on the bottom of the foot, which is a non-starter if we were related, if we had to rely on a bulk order of the previous devices that we were getting from National Shoe. So yeah, this is a nice way to showcase one of the other variants, and one of the nice things with 3D printing is it just changes it in itself isn't the solution. It just creates a framework for other solutions to be created. And that's where I think we need to stretch our mind a little bit with respect to understanding how orthotics work and how they can work perhaps more effectively for different conditions. So yeah, that's I'll turn it over to you, Ben.
Great. So yeah, when we transitioned through from the milled variant of this device to this printed one that you see on screen, we were able to get the same stiff on the lateral side, soft on the medial side outcome. But we also started to find some other significant benefits to it. This design is a heavy valgus posted device, which makes it quite thick and bulky. And we found within the first couple of prototype attempts that we tried with printing that they were fitting into footwear much, much better than the previous milled version. And so we looked into how we can make use of that. And that's one of the biggest benefits that we're seeing at the moment with this 3D printing method. So that's kind of where we're moving forward with this for a bit more general use. And this is what you'll start to see become available for ordering quite soon. So we're expanding what we've learned with the Voodoo devices, the textured devices that Michael and Kelly were just describing. With what we've learned from that, we're moving forward into some more general use soft shells. So the big development that has made this a lot more useful clinically quite recently is developments in material and how to use that material. So the flexible polyurethane material that we're using in these devices is not only flexible, but it can also vary the durometer of the material itself. So based on the printing temperature and the shape of the lattice structure, we can get anywhere from about a Shore A45 up to about a Shore 70 out of the same material. So the benefits that we're seeing, as I was saying, we get much better shoe fit than a milled or vacuum pressed device for a soft shell. The big killer app, the big difference that this makes is we can mix and match different softness zones, as Michael was saying, in a way that we can match anatomy and do kind of whatever we want with those zones of firmer or softer. Some of our other research has been showing for a couple of years now that the most effective orthotics are not necessarily the most supportive ones, but the most comfortable ones. And so by mixing and matching the different softnesses, we can make a very comfortable orthotic and sneak some support into it where it matters most. So we can get stronger support without impacting the comfort so much. And as Michael was describing it, it's another tool in the toolbox. A couple of the benefits that we've seen, and don't know how well you'll be able to see this on screen. Yeah, not great. If anyone's familiar with working with AmFit in-clinic manufactured orthotics, one of the types of milling blanks that AmFit produces has a firm material around the perimeter of the heel, and then soft through the center of the heel and the whole rest of the milling blank, which is a fairly useful design for a lot of cases, but it's limited to being just that specific horseshoe. With the printing, you can see on the Voodoo type, it has a solid heel counter around the sides, so we can have that support to the heel fitted specifically to that patient, while having the rest of it soft and compliant where we need it to be. So yeah, we can accommodate things for comfort, and gives us a lot of variables to play with to get that kind of comfort. And you can see in this image just the differences in printing density to get different softnesses. Now I'd like to hand this over to Alex now to talk about some of the practicalities of what this is going to look like going forward.
Hey, Ben, thanks. So, as everybody's been saying, the new 3D printing technology really showcases not only the benefits, but the necessity in our profession of measure twice and cut once. So, as always, taking a good scan or cast is really, really essential. But in addition to that, as you've seen with these devices that we're holding up, we really need a couple extra measurements to make sure this is truly just a plug and play device. That we have a mix of clientele and a lot of a lot of our clients don't have access to grinding wheels or lab equipment. So the option to modify a soft shell becomes really limited. With this, it really opens up that soft shell device feel and function to a lot of clients that don't have access to that lab equipment. So in order to make that actually functional, getting measurements from the patient during the assessment is really, really essential. Now, I've just got a quick little diagram here, and I'll post it in the chat. There we go. But this gives you a quick overview of what kind of measurements that we'll need, not only for the 3D printed ones, which they are supremely important for, but also for any soft shell. Because again, with that, with what we've learned from 3D printing, these measurements become very useful for any softer shell material that we're making. And it means less adjustments for your patients, less trips for them coming back in to see you, and just happier and more effective devices, or sorry, happier, more compliant patients and more effective devices at the end of the day. So, in terms of what measurements are going to be mandatory, if you can see the image that I posted, or I'll hold up my little sheet again here, really the most important thing is getting the narrowest part of the footbed that the orthotic is going to be sitting in. Now, you can get this measurement really easily by just grabbing the patient's shoe, taking the liner out or their existing orthotic, and get a quick tape measurement of what you can see as the narrowest part of the shoe. And in addition, we need the length of that measurement or the distance that measurement is taken from the heel. So if you can see again on the diagram, I'll hold that a little closer, narrowest part of the shoe, and then the distance from the heel. So that's really important for all of our, any of the orthotics that have full contact with the bottom of the shoe. And it means that whether it's a rigid plastisode or an EVA or one of these 3D printed devices, you're going to be able to take that orthotic and slip it right into the shoe, no muss, no fuss, and just more comfortable at the end of the day. So that's pretty much the nuts and bolts of the differences clinically and how you order them. In terms of how you treat them clinically, what conditions they're effective for, there's specific use cases like the texturing applications and the possibilities for that. There's the specific conditions like the NEO-A trials and research that Michael Ryan has been doing. But in general, using the 3D printed device is going to be, like Ben was saying, functional for a lot of just what you would use any EVA or rigid plastisode or other soft shell materials for. I've always, to my patients, kind of likened it to the difference between a traditional spring form mattress, going with something like graphite or polypropylene, and a foam-based mattress, right? So having something that just functions and feels different under the feet, having access to that in terms of being able to have it fit into footwear is a huge advantage for all of our clients. So we're still currently in a bit of a beta phase, which is why this is not released to everyone quite yet, but this is going to be available pretty soon to order, as Ben was saying, and it's good so that you all know what kind of measurements we're expecting to see when you do start to place orders for these. Okay. So that's basically the nuts and bolts there. The last thing I'll mention is, as you can see in the picture there, and I think I actually have that orthotic that picture was taken from, adjustments do happen. They're still going to happen with 3D printed devices, as with any other device. And it's important that, if you do have lab equipment, that you don't really want to make any adjustments to these, at least no adjustments that are going to be functional long-term, because as soon as you bypass that 1 or 2 millimeters at the edge of the device, you're getting into the lattice structure, and it's going to create a lot of weakness through the material. So the nice benefit about 3D printing, just as it has a good use case for research, it also means for adjustments and other major changes, we can remake these, and it's a lot more efficient than a traditional manufacturing. So, at the end of the day, it's a device that's going to be, easier to use both on your side and for the patients, versus some of the traditional devices. And we all know that more compliant and happier patients means that you can grow your business. Anything to add there, Ben?
Just one or two other things. One, you can see in this earlier slide the different softness zones. We've learned that the different lattice structures, the different softness of the material, doesn't work quite the same way as different durometers of foam materials. There is a bit of a thickness component to the softness. So when you get down to very thin, like 3 millimeters or so, the difference between a very soft lattice like that versus a very firm lattice, the difference becomes less and less the thinner you go, which is a bit of a different way of approaching softness than what we're all used to with materials that have different durometer. So yeah, that's a consideration which we will all be kind of reconfiguring, recalibrating our ordering around.
For sure. And this is, we're still learning things, just even in the last couple of weeks, we've been doing some iterative testing with a couple people, and yeah, just new lessons every day, every week about how these relate to the things that we're used to and how they're going to change things. So the possibilities are pretty open and varied, with the option to have very selective zones of density within the device. But yeah, as Ben said, there are certain areas where if you have it too thin, it may not matter as much what the exact softness of the zone is. The difference in feel will start to decline, right? But for something like heel wells, where you could potentially have quite a high height depending on the shoe, you can get a heel well zone that feels quite soft. So a soft zone, what we call 7, surrounded by that heel stiffener, which would be closer to a 1 or even you could say a 0. Feels quite cushy underneath, and you're not sacrificing the shape of the actual heel cup to build up padding. So you're retaining the function of the device, but still getting a lot of that shock absorption that you're after.
Yeah. So moving forward, 3D printing is going to be part of Kiwi's offerings. We're continuing to experiment and learn, and we'll be expanding access to this. So what this is going to look like going into the future, we are going to see further developments with these fused deposition soft shells that we've been working with. We're going to see further developments with these as we learn. You'll start to see those become available in the order form in the near future. And it's a new tool in the toolbox, so we'll be learning, and we invite you to experiment with us. In a lot of cases where you have a particularly difficult patient and difficult case come across your desk, and you're not necessarily sure what to do for that patient, or not sure how to achieve what you want to achieve for that patient, call us up, and in some cases, a printed solution might be part of the solution for that patient. Eventually, at some point, you will see the lab add hard shell powder bed printing as an alternative to polypropylene. There will be a tipping point where that does become a worthwhile offering. And what you can count on is that Kiwi won't just be presenting or forcing 3D printing as just because. If we're offering a 3D printing solution, it will be because it is clinically relevant in one way or another. And you can count on us keeping our traditional methods available long into the future. Even in the future when 3D printing is a much more common manufacturing method for us, we will still be maintaining the skills and the equipment to do things the way we've done them before, because it's a new tool in the toolbox. It's not replacing the old tools. I'm not throwing out my hammer just because I got a really cool new cordless drill. Yeah, another way to do what we need to do for our patients. So on that, I'm going to close up the presentation and move into some questions. So there's already a couple of questions here in the chat, both from Paul. Hey, Paul, how you doing? So Paul asks, does the 3D printed Voodoo cost more to your customers than the traditional CFO? On the manufacturing side, no, it does not. As to the clinical side, I don't believe the clinics are charging more for that than the traditional, are they?
Nope.
Yeah. So, yeah, on the manufacturing side, to kind of broaden that question just a little bit, we haven't established specific pricing for 3D printed devices yet, but the expectation, the anticipated pricing will be same or less than a direct milled EVA device. And there will be some cost savings actually compared to a vacuum press device, because on a vacuum press, most devices have two presses. So there's the shell and the arch fill, which are priced separately. With the 3D printing, there is no need for the arch fill, so that's one less line on the invoice. And then also from Paul, so are you suggesting we could also be taking these measurements when dealing with direct milled/molded orders? If so, how do we get this to the lab so that all measurements are accurate? Yes. In fact, in the fairly near future, there are going to be fields on the order form to put these measurements. We've been beta testing this with a couple of our clinical partners, and it's really quite a straightforward set of measurements. As Alex was demonstrating, just get a flexible tape measure, shove it in the shoe, and measure the width, and then where that width is. Those fields will be on the order form, and it'll make your life in clinic a fair bit easier to just pop those in. So yeah, there we go. From Tennille, what is the longevity of the PU that you are using to print? Is it about the same as poly? At this point, this material is fairly new to clinical use. We don't actually have a final figure on this. We have devices that have been in use for 8 months now and are still performing well. The CAD partner that we're working with to create these devices, they have a little bit longer. They have devices in a little bit longer service through some of the other users of this in Europe, and they're seeing at least 1 year to a year and a half longevity in most use cases. So proportional, similar to other soft shell longevity. They will not, well, I won't say they will not be. I would be really surprised if they were the kind of indefinite lifespan of Polypro. But they're looking about the same as an EVA soft shell so far.
Ben, I've got maybe a question that, or a comment that you might be able to speak to a little bit more. I think you alluded to this in the talk, that from a manufacturing standpoint, one of the advantages that 3D printing has is the ability to kind of integrate these different hardness zones within the device. And that also means that we can integrate additions and extensions directly within the shell. And so there's certain features that you might expect to have outside of that, like a met pad, for instance, or a 2.5 extension. But what this will allow us to do is to have certainly a lot more. We've all like, in fact, the irony here is when I was going to say be more consistency in the production of these, even though we've used a 3D printed measurement tool to ensure these, because these are still aspects that are ground by hand by skilled technicians in the manufacturing steps. But of course, when you can replace that with just a computer design where the object is, constrained and defined ahead of time and then just printed out, be kind of an interesting and new approach, and to see how we can vary the shape of a met pad even to match, let's say, if anyone takes pressure measurements for their patients during their gait, it'd be interesting to then say, well, I need a met pad that's shaped like this. And you do a drawing perhaps on the bottom of the foot, send over the color image from the 3D impression. Conceivably, we can recreate that sort of again to the anatomy, or to the kinetics, I guess, in this case, of the patient. So I think we're just getting started with some of the applications that 3D printing can make, which will help just help the clinicians have more tools, help the patients experience better relief. It makes it easier for the lab to execute that. So it's sort of a nice example of a truly like human-centered solution when done properly.
Yeah, getting the additions and modifications printed straight into the shell is of benefit. Like you said, we can vary the shape to get that in there. Now, some of that we have had the ability to do that with like direct mill, to get that shape milled into, say, an EVA device or even a PolyPro device. But I've never really liked using that approach, because who wants a 55 durometer met pad? That's a pretty hard, uncomfortable met pad. But with the mix and match zones, we can have a firm supportive shell and then a soft met pad of whatever shape. There's actually one particular patient that I have in mind specifically for what you're describing, Michael. About every 2 or 3 years, this one patient comes back to one of our clinics for new orthotics. This patient has a congenitally very short third metatarsal. So their 5 metatarsal heads don't all line up. You've got 1, 2, 3, 4, 5. And so every time we need to get on the bandsaw, cut the shell shorter, grind the met pad around that piece, and it always has to be touched up in clinic at the dispensing. If we just map that met pad around the anatomy, we can get that shape to fit the same every year. So yeah, next time that patient comes to clinic, they got a surprise coming.
Nice.
Do we have any more questions out there? It looks like we've got about 5 minutes left in our time slot.
Certainly, as people have questions, they can reach out to, any one of us on the team as they might pop up, or you see certain use cases or other ads by other venture companies that are proposing to do XYZ from a 3D printed device, feel free to send them to us and say, hey, can I get something like this? Maybe. Depending if it's actually going to benefit anyone. So, yeah.
Yeah, I think one of the big take homes. Oh, we've got another question here. Great. Tennille asks, will we be able to order both geometric and anatomical shells with the 3D? Absolutely. One use case where I think this is going to be particularly useful actually is for amputations, like hallux amputations, transmetatarsal amputations. We'll be able to get a really nice distal transition around the residual leading into the shoe filler. A lot of the time with current methods of making amputation fill orthotics, you have the orthotic and then a filler that's just a lump added on top, and it never really blends all that well. I think with printing, we'll be able to get a really nice kind of a soft transition into the filler zone. So for the most anatomical of anatomical cases, yeah, I think it's really a good use case. Okay. Well, on that note, yeah, I believe it's time to wrap up. So, as one of us said at some point, we're 3D printing. Its use is really only limited to our imagination, and as it turns out, that imagination does tend to be a bit of a limiting factor on this. So keep imagining, and we're going to keep imagining and seeing what we can do with this technology. Now that we have this in our toolbox, as the interesting and tricky cases come across our desks, we're going to continue thinking of how this can contribute to solutions for patients, and that's where we're really going to learn how to make the best use of this new technology. So thank you all for attention, participation, and as Michael said, reach out to us at any point with any questions. Right.
Thanks, everyone. Thanks, Ben,
everyone.
Alex, and Kelly.
Thanks, everyone.
Have a great day.
And I'll be making the recording available for anyone that either came on late or wasn't able to come on today. So I will send that out to everybody. Okay.
Thanks, Alex.
Thanks all, and have a great day.